Nearly 2 billion years ago, deep in the ancient crust of what is now Gabon, Africa, an extraordinary and almost unimaginable phenomenon unfolded. A phenomenon so rare and improbable that it would take human scientists until the 20th century to even recognize its existence. In 1972, French nuclear experts, while examining uranium ore from the Oklo mine, stumbled upon a mystery that would send ripples through the world of science. The uranium samples they analyzed did not fit expectations. Instead of the usual ratio of uranium isotopes, the ore exhibited a significant depletion of uranium-235, the isotope crucial for sustaining nuclear chain reactions. This anomaly could only mean one thing. Sometime in the distant past, nuclear fission had occurred naturally, without any human intervention. Thus began the unraveling of the story of the Oklo natural nuclear reactors, the only known natural reactors on Earth, and a testament to the profound intersection of geology, chemistry, and physics. To appreciate the magnitude of this discovery, it is important to understand the fundamentals of nuclear fission and the conditions necessary for a reactor to operate. In human-made reactors, uranium-235 is the fuel that, when bombarded with neutrons, splits into smaller atoms and releases energy. For a chain reaction to be sustained, the uranium must be sufficiently concentrated, and there must be a moderator, usually water, to slow down the neutrons, increasing the likelihood that they will induce further fission events. Additionally, the presence of neutron-absorbing substances, known as poisons, must be minimal. Otherwise, they halt the reaction prematurely. In the depths of Oklo, nature had, against all odds, assembled these ingredients. Around 1.8 billion years ago, the concentration of uranium-235 in natural uranium was much higher than it is today. As uranium-235 decays more rapidly than its sibling isotope, uranium-238, the ratio was then about 3% compared to today's 0.72%. This was just enough to reach the threshold for a self-sustaining chain reaction, provided the other conditions were met. The uranium ore at Oklo had accumulated to unusually high concentrations, and groundwater percolating through the rock acted as a natural neutron moderator. The operation of these reactors was nothing short of miraculous. As the chain reaction commenced, heat was generated, causing the groundwater to boil away. Without water, the moderation stopped, and the reaction shut itself down. As the rock cooled, water seeped back in, restarting the process. This automatic cycling kept the reactors running intermittently for hundreds of thousands of years, with on and off phases dictated entirely by the natural dynamics of heat, water, and rock. Geologists identified 16 separate reactor zones at Oklo, each with evidence of sustained fission, altered mineralogy, distinctive temperature profiles, and the presence of fission products and transuranic elements such as plutonium-239. The reactors appear to have operated with remarkable stability. Each zone maintained criticality, balancing neutron production and absorption, while the natural feedback mechanisms prevented runaway reactions or catastrophic meltdowns. Analysis of the fission products provided a window into the reactor's past. The isotopic ratios of elements like neodymium and ruthenium match precisely what would be expected from long-term nuclear fission. Plutonium was produced and consumed in situ, further supporting the conclusion that these were genuine nuclear reactors, not mere flashes of criticality. The efficiency of fission and the containment of radioactive waste were such that, even after 1.8 billion years, most of the radioactive materials remained locked within the reactor zones, unable to migrate far from their point of origin. The unique geology of Oklo played a vital role in this containment. The host rocks possessed chemical properties that bound fission products and transuranic elements, preventing their escape into the wider environment. Groundwater movement was limited, and the mineral matrices acted as natural barriers. In a sense, Oklo demonstrates an ideal model for nuclear waste disposal, where geological and chemical stability can preserve radioactive materials for eons. The reactors operated at moderate temperatures, estimated between 150 and 500 degrees Celsius. This range was sufficient to drive chemical reactions and alter minerals, but not so extreme as to disrupt the reactor structure or lead to uncontrolled melting. All of this occurred without any engineered safety systems, just the interplay of rock, water, and uranium. Over their lifetimes, The Oklo reactors generated energy equivalent to that of several modern nuclear plants. The heat produced drove hydrothermal circulation, altering the surrounding rocks and creating lasting signatures that scientists continue to study. The site has become a natural laboratory, offering unique insights into the operation, containment, and long-term behavior of nuclear reactors. The implications of Oklo's discovery are profound. It forced scientists to reconsider the boundaries of nuclear physics and reactor design. If nature could assemble and operate a nuclear reactor with no human intervention, what does that say about the potential for simple, inherently safe reactor designs? Oklo's reactors relied on the most basic physical principles: moderation by water, self-regulation through thermal feedback, and containment by stable geology. These lessons have influenced the design of modern reactors that seek to use natural processes for safety and efficiency. Oklo's reactors also offer a glimpse into questions that reach beyond Earth. The discovery suggests that, given the right conditions, natural nuclear reactors might arise elsewhere in the universe. On planets or moons with uranium-rich deposits and liquid water, similar processes could unfold, contributing to planetary heating or driving chemical evolution. This possibility has intriguing implications for the study of astrobiology and planetary science. Remarkably, the region around Oklo shows no evidence of lasting harm from the ancient reactors. The natural containment and stability of the site have protected the local ecosystem, with no signs of unusual radiation or genetic damage. This stands as a powerful testament to the ability of natural processes to manage nuclear energy safely over immense spans of time. In sum, the Oklo natural nuclear reactors are one of nature's most astonishing achievements. Their existence reveals the delicate balance of forces that can, under rare circumstances, give rise to self-sustaining nuclear fission. They operated safely, efficiently, and with remarkable containment, offering lessons for science, engineering, and the stewardship of nuclear materials. The story of Oklo challenges our understanding of what is possible and continues to inspire new research into the fundamental laws of nature. It is a reminder that the Earth itself is a laboratory, capable of surprising us with phenomena that defy expectation and deepen our appreciation of the world's hidden wonders.